Science on Surfaces.
Hello there and welcome to this podcast, Science on Surfaces, Tips, Tricks and Tools, with me, Malin Edvardsson. So today we will talk about methods and technologies used in a biointerfaces lab. We will talk about which instrumentation that is used and why. And here with me in this call I have Dr. Jenny Malmström, Senior Lecturer in Chemical and Materials Engineering at the University of Auckland in New Zealand. Welcome, Jenny.
Thank you.
It's great to have you here from the other side of the planet.
I know, it's crazy, right?
It is. Fantastic technology. So how are you today?
I'm good, thank you. Sun is just about to set here, so yeah, it's nice.
Great. So before we dive into the topic of instrumentation, let's talk a bit about your research. I read on your website that your research is all about interfaces. So what is it that you do?
Yeah, so it is really a lot about interfaces, so both in the sense of being at interfaces between disciplines, so between materials and biology, and physical interfaces. So we work a lot with making engineered interfaces to try to better understand, or ideally, perhaps in the next step, control biology. So in particular, stem cell biology. Mm-hmm. But we're also interested in using biology as an inspiration to template or design advanced materials. So we're sort of, the biology is sitting in the middle and then the materials on either side in our little world of interfaces.
So what will the materials be in the end, I guess somewhere in the future? What are you aiming at? What kind of materials?
So on the side of understanding biology, a lot of the things that we do is really developing model systems to try to pinpoint some specific biological function that we want to understand better. So those are quite highly engineered 2D model interfaces. So not something that's going into a patient or anything like that. So just basically creating a surface that can work as a research tool. Mm-hmm. And then on the other side of using biology as an inspiration for some advanced materials, we're interested to try to pattern magnets by using principles of self-assembly, or to use sort of hijack biomolecules and proteins for something else than their day job to do some functional
Did you say hijack them?
I said hijack, yeah.
Yeah.
So I mean, proteins do lots in their day jobs, but they also have other functions. So, for example, a lot of proteins are in fact piezoelectric. And so that's something we're really interested in looking at and seeing what we can use that for in the future. Mm-hmm. So a lot of fundamental research, aiming to hopefully do something a bit more applied in the future.
Yeah. So will the applied work be in your group, or are you doing the fundamental work and then the results will be utilized by some other groups? Or do you span like the entire range from fundamental to applied work in your group?
So most of the work in our group is quite fundamental. I think that's because that's where I often find the most interest. But for some of the projects, we're going a little bit further. So for example, with this idea around the piezoelectricity of proteins, we're both doing some really fundamental work, trying to figure out what structural properties in proteins that elicit this piezoelectricity. And we're also trying to just grab some different biological materials and see what we can make with them, which is more applied, obviously.
Mm-hmm. So you talked about surfaces and the interfaces. So what surfaces are you using or looking at? If you go into the interface, sort of, what did you have there in the interface?
Yeah, so one example, which is probably our most interfacey project, is where we're trying to make an experimental model system to be able to look at both growth factor release, so how growth factors signal in cells, and the process of mechanotransduction, so how cells sense the mechanical properties of their surrounding. And so to do that, we're making a thin blockopolymer film, and blockopolymers self-assemble into these beautiful nanostructures, and then we're along with the block of polymer, we're self-assembling proteins in this block of polymer film. So they go into one of the domains. That should be a growth factor, but at the moment it's just a very sturdy model protein that we can actually, measure and measure the release of and so on. And then on top of that block of polymer film, we're putting another layer to try to control and slow down the release of the protein. And then on top of that, the cells will come in the next step to try to then release the growth factor in a controlled way.
Okay. And the block copolymer, is that on gold or kind of glass, or how do you attach it?
Yeah, it's actually on gold. So
Oh.
it's something that's really intriguing because it doesn't work on anything else than gold.
Oh, really?
So we've been through like every chemistry in the book. Not really, but we've been obviously tried glass and silicon, and then we've tried different modifications on glass and silicon that you would expect to give you a similar behavior, a similar contact angle as gold. But gold is the only thing that's been successful so far.
Oh, wow. Yeah, that's intriguing. It's so then once the cells are added, what do you expect from them? I mean, do you expect a certain behavior from them then, or what's the end goal?
Yeah, so the end goal is to try to make a surface where the cells actually have to pull on the surface to release the growth factors, and that would allow us to study the synergies between mechanotransduction and growth factor signaling.
Okay.
But in this project, we have encountered a lot of challenges.
Okay.
Yeah, I mean, it is on paper a very challenging project to start with, and then there's been new challenges that have surprised us along the way, for sure.
Mm-hmm. So what are those? Do you have any examples of challenges?
So actually just the quality of the block copolymer film and how sensitive that is to the interface, both, the air polymer interface and then the polymer gold or polymer something else interface. That's caused challenges. So we're not working with a straight solvent. We're working with a solvent mixture to be able to both solubilize a protein and the block copolymer. So it's 3 different solvents. It's benzene, methanol, and water. So that mixture and the block copolymer and the protein makes it all very, very sensitive to environmental factors. So one day things work, and then the next day the humidity is too high, things don't work so well, and so on. So from the very, very early stages, things that we thought were going to be relatively straightforward, we've had some challenges.
That's research for you, right?
I know, right?
Challenges and challenges. Okay. So this is is this like the big project that you do, and then all activities are related to this, or do you have any other projects as well?
Yeah, we have a few other projects as well. So another thing that we have done quite a bit on recently has been looking at gels, hydrogels, again for understanding cell biology. So we have worked on trying to make hydrogels where we can control the viscoelastic properties. So often synthetic hydrogels are essentially purely elastic. And then we've been trying to dial in a second component to make them more viscous in a controlled way. And we've been trying to pattern that spatially. And we've also worked with hydrogels where we've tried to control the stiffness over time. So we've made conducting hydrogels, and we try to then apply a potential, and then the hydrogel changes its properties. Mm-hmm. So some things like that we're playing around with.
Yeah, and that's just for fundamentally understanding or trying to control, or do you have an end goal with that as well?
Yeah, so that's also related to the questions around mechanotransduction, so how cells sense their environment. So a lot is known about how cells respond to stiffness, whereas less is known about how cells respond to the viscous cues. I mean, it's starting to come up now, but there is still a bit to find out there. And also, there's not that many materials where you can just change the stiffness on cue, so to speak. So that's why we've been interested in making a hydrogel where we can just change the mechanical properties by applying a potential.
Okay, that's interesting. So you work with polymers, proteins, biomolecules, cells, spanning quite a wide range then of, I don't know, kind of molecules, I guess you would call it. So,
Yeah.
so if we move into the instrumentation that you use, I mean, what technologies would you use to characterize all these materials and the processes that you're interested in understanding?
Yeah.
Because there's
So
like a wide range of of instruments in your lab.
yeah, there is actually, there's lots of instruments that we use that are not in our lab. So we work quite collaboratively and use instruments all over the place, both at the university and more widely in the country. Some of the things that we use the most is probably AFM and different modes of AFM as well. So it's like functional modes where you can use to look at the magnetic properties across the surface or the piezoelectric properties and so on. And then for surface characterization, obviously we use things like contact angle instruments, XPS a little bit, QCMD, and things like Raman and FTIR and so on. And then for the gels, there's a lot of mechanical testing, so tensile and compression. We do a lot of just AFM mechanical testing as well, and rheology. Those are some of the workhorses, I think.
So there were a few different categories of technologies that you mentioned. Like XPS is like a chemical component characterization, I guess. So I guess, is that something that you would start with before you start layering, or is this something that you, I mean, I'm not so familiar with this, but can you do it along the way, or can you only do it on the solid surface that you start with?
Yeah, only on the solid surface. Well, you can do every stage of the solid surface, but it's an ultra-high vacuum technique. So you will. It's not like in the QCMD where you can look at the real-time changes or anything. Yeah.
So you do it on the sort of the surface that you start with, and then once you start adding polymers and stuff, then you move on to other characterization techniques.
Yeah, so sometimes we would do XPS at the end state as well. So for example, in this project with the block of polymer with the proteins inside, we wanted to show that we really had proteins inside. So we put our sample in the XPS. We couldn't detect any protein because it's hiding inside the film, and XPS is very surface sensitive. And then we leached the protein out and measured it again, and then we could in fact detect the protein on the surface.
Oh, really?
So yeah, we often use it at several stages, but it's one of those techniques also that has a slightly, I guess, higher skill to use. So our instrument is technician run, and so you have to book in a time, and it's quite high user charges and so on. So it's something that we use once we think we know what's going on, then we go and add the XPS that hopefully confirms what we think we have.
Okay.
And if it doesn't, we go back to the drawing board.
Yeah, okay. And then for the AFM, I guess that is a bit easier to use than the XPS. More like you can just go and, have a look.
Yeah.
What do we have here? But you mentioned something. I mean, I know that you can get sort of this like structural properties or topographical, like a topography from the AFM. But you also mentioned that you could sense the magnetic properties or piezoelectric properties or something like that. How does that work?
Yeah, so it is a whole raft of functional modes in AFM actually that you can do that just add a little bit of complexity. So there's a varying amount of complexity, I guess, but a lot of them have in common that so normally if you just image in AFM, you would tap along your topography and detect the topography along a line. And a lot of these extra functional modes, they add a second passover, where you follow the topography at the set height, but you're not actually within within contact of the surface. So say that you move up 50 nanometers or something. And so then you're sensing the forces at that range. So magnetic forces or electrostatic forces are
right.
examples of things that you can measure there. So then to measure magnetic interactions, you'd have to have a magnetic tip. Or to measure electrostatic interactions, you'd have to have a conductive tip, and you apply a bias between the tip and the sample.
So basically then you can, by scanning like from a distance or at a distance, can you then detect where you have those piezoelectric proteins? Is that visible?
So the piezoelectric AFM is a little bit more complicated. It's actually a contact mode. So you actually resonate the cantilever in contact with the sample, and you look at the contact resonance and how that changes. So that gets kind of tricky, and that's part of the issue, I think, with using piezoelectric force microscopy on proteins, because they obviously not always robust enough for those contact interactions, and the piezoelectric response from a protein is frightfully small. So it's really hard to know what you're really getting out of an AFM measurement when it comes to piezoelectric force microscopy on proteins. That's another thing we learned the hard way.
Yeah. Okay.
Yeah. But for magnetic properties and electrostatic properties, is more straightforward. You're getting both the topography by doing one scan, and then the next scan you're getting those longer range interactions, and you can then overlay those two images to really correlate what's going on in your sample.
Okay. And then you measured contact angle. That's also something that you do at the beginning of the sort of layer buildup, or do you do that along the way as well after each sort of layer?
No, so that's, I guess, something that we use. I mean, I guess that's an instrument that's really easy to access for most people. And so something that you can use for really preliminary investigations of surface chemistry before the XPS, for sure. So, for example, I mentioned we evaluated lots of different surface chemistries to try to see if the block of polymer would assemble on anything else than gold. So, for example, in that exploration, we would have done a lot of contact angle to see if we deposited what we thought we deposited on our various surfaces and so on. And we're also doing some layer by layer assembly on top of this block of polymer film. So one student is doing contact angle to verify that the chemistry is changing between the different layers that we're building up. So things like that, yeah.
And then so XPS AFM, the contact angle, you mentioned QCMD as well. That's like a different character. It's more like a time result technology than the ones you mentioned that are more like a, it gets, what do you call that in English? It's like a
snapshot.
Sorry?
A snapshot.
Snapshot, exactly, snapshot. So this is for the build-up, following build-up of layers at the surface, or how do you use the QCMD?
Yeah, so at the moment we use it for these layer by layer systems to try to verify the things I'm building. So often, well, we've often doing both, like some imaging of the different steps, so doing AFM, but then obviously you're just seeing the top surface if you're doing AFM, and then we're also doing QCMD to try to verify how the layers are building in real time. We're not actually depositing in a similar way when we're making the samples. We're spin coating to deposit, so obviously there's a discrepancy between what the sample really looks like and what we can look at with the QCMD. So I think they're quite complementary. And then we've also used QCMD to look at just different protein interactions at surfaces and enzymatic degradation of proteins and so on. I mean, of course, I love QCMD, right?
Of course, who doesn't?
Yeah.
So are you using any other time result technologies at all? Like ellipsometry or I don't know, optical?
But not much. We have an ellipsometer across the road in chemistry. We haven't used that for time resolved measurements. It doesn't have a very good flow cell, I believe. What we are using though is for to measure the release of molecules from the block of polymer film, we're using fluorescence spectroscopy. So we're
Okay.
putting like a tag on the protein and then getting to the release. So I guess light-based methods are useful in that way.
Yeah, and so then you get that's time results. You get like like a film or something like that, so you can follow
Actually,
the release. Or
well, I guess time result was probably poorly stated. It feels time result to us because it's resolving the things that are happening at the times that we're interested in, but it's actually manually recording a spectra every time we press the button or so on. So maybe we're taking a spectra every 2 minutes or yeah. So time resolved.
Yeah, good enough rate for that process.
Yeah.
Okay, so what else did you mention? XPS, AFM, contact angle, QCMD, fluorescence.
So mechanical testing and rheology is something else that we're doing in particular on the hydrogels project, because that's quite central. And the hydrogels are too thick to really attack with the QCMD, so we've had to use other methods there.
So what thicknesses are we talking about?
So often we're making them sort of macroscopic chunks. Sometimes we're making them maybe 200 micrometers or so. So still thick on a QCMD standard.
Yeah. And then for the mechanical testing, is that like some sort of probe? Then piercing, or how would that work?
Yeah, so we do quite a lot with the AFM again. So you can do a force distance curve with the AFM. It doesn't work for all hydrogels. Sometimes they're simply too sticky, so you get stuck even if you have to do these measurements in liquid. So other things that we also do is for bigger gels, we're doing tensile testing. So just you make like a dog bone shape and you pull it. And also compression testing, which is, I guess, the same principle as doing it with an AFM. You're just not doing it from a cantilever, so you're applying much larger forces. The compression curve.
Okay. So these are all like standard methods that you are using more or less all the time, would you say?
Yes. Yeah.
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 And are there any methods that you only use now and then? I don't know, to verify like some specific aspect of whatever questions you're asking or so.
Yeah, I guess there's lots of things that we only use now and then, but I guess an example of that might be scattering on the beam lines. So we can do neutron scattering and X-ray scattering on the beam lines in Australia, and that only happens when we get awarded beam time.
Yeah.
Yeah.
Yeah, okay, so then you have to travel to Australia to do that as well. So I can see that's not every week you would do that, maybe?
No, and the cycles of getting, so you put in a proposal and then it's like 6 months at least before the beam time is awarded, but often you're not successful in that round. So yeah, there's definitely a bit of hit and miss.
So what information do you gain from those measurements?
So you can do a few different things. Actually, you can do lots on the beam lines. They have all sorts of interesting. They even have XPS types and various microscopies and so on. But what we're using it for is just scattering through the gels mainly. So then we're getting structural information about the things that are scattering in the gel and what size range that is at. And so again, it's quite interesting to be able to use both X-rays and neutrons because they interact with the material in different ways. And then we've also done a little bit of magnetic measurements with the neutrons, so polarized neutron reflectometry. So then you're looking at the reflection of the the neutrons from the surface. And you can also do that with X-rays and do, for example, grazing angle scattering. So then you're getting a different set of information than if you're shining the X-rays all the way through a sample.
Mm-hmm.
So then you can start getting some structured information about ordering instead, either ordering in layers from the sample or ordering in plane with the sample.
Yeah. Okay. Oh, okay. I see. Okay. So would you say that the set of technologies that you are using, would that be considered like a standard range for a biointerfaces lab? Any instruments that stand out that you're using, or that others usually have that you don't?
I think there's plenty of instruments that other have access to that we don't. Maybe something that's very complementary, obviously, to something like the QCMD would be an optical real-time method like SPR or ellipsometry or so on.
Mm-hmm.
In regards to where we're located on the globe, I think the QCMD is what stands out as being quite unique to what we have.
Mm-hmm.
And also, I think some of the specialized modes that we're using on the AFM is also probably a little bit bespoke in how we're using them. So we're also combining electrochemistry with both with QCMD and AFM actually, which is nice. Otherwise it's fairly standard.
So I was wondering about, is it, to sort of stand out, or with the research that you're doing, if it's needed to have like some sort of unique characterization method, if that's really needed to have like a competitive edge on the work that you're doing, but maybe it's not that you have to have like an instrument that no one else has, or I don't know. What's your thoughts on that?
I don't know that you do have to have an instrument that no one else has. I think it helps to have access to fancy equipment and to the right equipment that can really answer the question that you're asking. I'd like to think that you could do research on you can do good research on different budgets, and that it's not all relying on what instrument access that you have.
Because I was thinking that it could also be the other way around, that it's not good to have something unique because no one recognizes it or understands it, and you would still need to prove your statements and conclusions with more well-known methods, maybe. I don't know.
Yeah, maybe. And I guess if you go down the track of building your own instruments, then I guess then the questions become centered around what instrument you're building, maybe more what can I answer with this kit that I built, then how can I answer the question that I have with whatever kit other people have built. So
right,
I guess there's two sides to that.
Yeah, exactly. Yeah, so you mentioned budgets. So I'm curious, if you were to say that you're starting up a new lab as a researcher and you have maybe limited funding, what would you advise such a person to invest in? You can only invest in so many instruments to start with. What would you recommend?
Yeah, I think it makes sense to invest in the small nitty-gritty day-to-day things that you really want to do in your own lab, and the things that you really need every week. And then you can collaborate for a lot of other things. So maybe set up the basics and then try to get, one or two nice pieces of equipment that's maybe unique to your research. So in my case, when I started my permanent position, the thing that I asked for was the QCMD. And so that's what we have, which is sort of the unique thing in our lab. The AFMs are actually core facilities, so they're sitting sort of centrally in the university and are managed elsewhere. And so, the other things that we bought were very simple things, like a schlenkline for the fume hood and a spin coater and pipettes and simple things that you need to make things every day and that you don't want to go across the road or even down 3 floors for.
Yeah, I can imagine so many things that you need for a lab.
Yeah.
pH meter and like your balance and you know all
Yeah.
those
There's a
things.
long list.
Mm. Um, so I was also curious if there are any like new like hot technologies that you know are talked about in your area of research that everyone wants or not.
I think for us, something that interests me, it has always been sort of combination techniques where you can measure one problem from several angles at the same time, or at the same sample.
Mm.
Um, so that could be, like with the QCMD, how you can apply perhaps a dry mass method on the same sample. And for us, when it comes to imaging, we're also really interested if we can try to resolve chemical information along with the structural information. So chemical information on the nanoscale is something that's interesting. And so there's some, I guess there has for some time been AFMs that can do Raman at the same time, for example. The spatial resolution has always been very compromised, but there are some new ways of doing this now that's bringing down the spatial resolution to what you can have used for with a traditional AFM, and so you can get chemical information at the scale of 10 to 20 nanometers. And I think that's opening up a different set of questions to look at. So I think techniques that open up to answer new questions, those are the really exciting ones.
Mm. Yeah, I can see that, and like what you mentioned, you get more information from one single measurement. Not only do you get more information, but you know that you're also looking at the same thing.
Yeah.
As it
Yes,
happens.
also in imaging, like in transmission electron microscopy, there are now available to actually look at molecules in a hydrated state in like a little cell with a tiny amount of water. And so that's really cool. You can start looking at dynamics. And with AFM as well, you can do video rate AFM in a much simpler way now than the high-speed AFMs that were developed a long time ago, which were very, very specialized instruments. So I think we're seeing a transition from things being too complex for the average researcher to use to making things more and more user-friendly, so that they're actually applied to more research questions.
Yeah, that's interesting. And I mean, I guess this. I mean, it really helps then with this to push the limits of understanding the world and creating the new materials and so on. If you have the tools to help you. Let's see what other questions I had here on my notes. No, I think I actually covered most of my questions. I was wondering, what's the most challenging thing to measure? I think you touched a bit upon challenges in the beginning, but that was more in terms of getting things to work and understanding, I guess. But in terms of measurements and finding a specific answer, are there any challenges there in terms of just doing the actual measurement?
There's always plenty of challenges, I think. But something that perhaps surprised us was, so I mentioned how we want to release a protein from this block of polymer film. And we needed to first establish the release rate to understand, I guess, what our options are in terms of controlling that release rate and adding some sort of capping layer on the film. And that simple question of what is the release rate was very hard. So we tried lots of different things that simply didn't work out. We tried enzymatic assays, which were a hundredth as sensitive as they should be according to the manufacturer. And what eventually ended up working was labeling the protein with a fluorescent marker and doing fluorescence spectroscopy. But it took us much longer. It sounds so simple, but it took us 2 years to get to that point.
Wow.
Yeah.
Yeah. But now you know the answer.
Yeah, exactly. Yeah.
Yeah. Okay. Anything that I missed that you would like to add that is key to instrumentation in a biointerfaces lab?
No, I don't think so. I think it was great. Maybe a piece of advice, I guess. I guess it depends on what where you are in the world as well. But here we're quite far away from everything, and our universities have probably less instruments than they do in Europe. And so for us here, it's really important to collaborate. And I view all of New Zealand as one university, more or less, and just travel to do stuff.
Great. Thanks for that advice, and thanks for sharing all this information. Very useful. So I want to thank everyone for listening to this episode with me, Malin Edvardsson, and Dr. Jenny Malmström, University of Auckland. And I also would like to take the opportunity to mention to those of you listening or watching that if you're interested in surface science or related topics, you should check out our blog, the Surface Science blog. Thank you.
Thank you.